In the previous video, we discovered the law of quadratic reciprocity by looking at the nearly symmetric table of Legendre symbols Q on P where P and Q are prime. Specifically, we saw that a pattern arose if we focused on where the symmetry was broken. Then we proved Gauss's lemma. Gauss's lemma is an important stepping stone for the proof of quadratic reciprocity presented in the book. It's worth noting that there are about a couple hundred different proofs of quadratic reciprocity, and so this is one of those theorems that can be a launching point for all types of mathematics. Theorem. If P and Q are distinct odd primes, then we have P on Q is equal to Q on P, unless P and Q are both equivalent to 3 modulo 4, in which case they are different. Notice that in the case that P and Q are both equivalent to 3 modulo 4, we could also say that P on Q is equal to negative Q on P. To prove the theorem, let mu1 be the number of multiples of Q in the set Q 2Q up to P minus 1 over 2 times Q, whose least residues modulo P are negative. And let mu2 be the number of multiples of P in the set P 2P up to Q minus 1 over 2 times P, whose least residues modulo Q are negative. Then by Gauss's lemma, we can calculate each of these Legendre symbols in terms of mu1 and mu2. We can then multiply these equations together. From this equation, we can see that the Legendre symbols are the same if and only if mu1 plus mu2 is even. In other words, the Legendre symbols are different if and only if mu1 plus mu2 is odd. Therefore, our goal is to show that mu1 plus mu2 is odd if and only if P and Q are both equivalent to 3 modulo 4. Our proof will be geometric. We will find two ways of counting the same set of lattice points in a certain region. The first time we count them, we will show that there is an odd number of points if and only if P and Q are both equivalent to 3 modulo 4. The second time we count them, we will show that there are mu1 plus mu2 lattice points. Putting these two statements together will give us the result. The region we will be investigating is a diagonal strip of a rectangle in the plane. The rectangle is defined by these equations. The diagonal strip will be the region between these two lines. We have written the second equation in a non-standard way to demonstrate the underlying symmetry. However, for the sake of visualizing the picture, we will also write it in slope-intercept form. From this, we can see that the two lines are parallel. The key observation is that if the lattice point Mn is in the region, then the reflection of this point through P plus 1 over 4, Q plus 1 over 4, is also a lattice point in the region. To see that this is true, we just need to examine the defining equations. There are a lot of algebraic steps involved in the calculation, so we'll stick to the high-level overview. If the point Mn is in the region, then the points Mn satisfy these equations. The first two equations can easily be rewritten to show that the point M'N' satisfy a similar equation. To see that this is equivalent to the original equations, we need to use the fact that M' and N' are integers. We do not introduce any new integers into the interval if we change the lower limit from 1/2 down to 0. The upper limit is an integer, so we do not lose any lattice points by reducing that limit by 1/2. The third inequality can be shown through direct substitution. Since the points Mn and M'N' are reflections of each other, there will be an even number of lattice points in the region provided that the reflection point is not a lattice point. In other words, the only way we can get an odd number of lattice points in the region is if P plus 1 over 4, Q plus 1 over 4 is a lattice point. And this can only happen if P and Q are both equivalent to 3 modulo 4. And this completes the first way of counting the lattice points. For the second way of counting the lattice points, first notice that since the equation of the diagonal is y equals Q over P times x, and since Q and P are both odd primes, that there cannot be any lattice points on the diagonal. Let's count the lattice points Mn in the region below the diagonal. We will fix the x-coordinate at some integer m. The y-coordinate n must lie between the two lines so that this is the required condition. After some manipulations, we can rewrite the condition in a more compact manner. Notice that the term in the middle is equivalent to np modulo m. Furthermore, it shows that there is a point in the region below the line if and only if there is a number between negative q over 2 and 0 that is equivalent to np modulo m. This is the same as saying that the least residue of np modulo m is negative. In other words, each lattice point in the region below the diagonal corresponds to a point in the set P 2P up to Q minus 1 over 2 times P, whose least residue is negative. Also, each of these terms whose least residue is negative must appear as a lattice point in the region since we can find an integer m that satisfies the inequality. Recall that mu2 was defined as the number of values in the set that have a negative least residue. This means that there are mu2 points in this region. The same argument works for the upper region, which would show that there are mu1 lattice points in the region above the diagonal. And therefore, there are mu1 plus mu2 points in the region, which completes the second way of counting the points and completes the proof. Since this proof is long and involves a lot of ideas, let's recap the main steps of the proof. We started off by using Gauss's lemma, which states that we can determine the value of the Legendre symbol P on Q by determining mu1 and mu2. The values mu1 and mu2 correspond to the number of negative signs in specific sets of multiples of Q and P. We used this to show that P on Q and Q on P are different if and only if mu1 plus mu2 is odd. We then counted the number of lattice points in a particular region in two different ways. One way showed that the number of lattice points is odd if and only if P and Q are both equivalent to 3 modulo 4. The second way shows that the number of lattice points in the region is exactly mu1 plus mu2, and this gave us what we needed to prove the result. This proof is a little bit complicated, and you may need to watch the video a couple times to really understand it. Here's a full summary of the example that was used as the model with explicit calculations. It might help to work through the steps of the proof using this image to explicitly see where all the different values come from.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.